Welcome back to another explainer. Today, we're rolling up our sleeves and getting our hands dirty with some Haskell programming. Look, if you've spent any time building text parsers, especially in a functional language, you know exactly what I mean when I say it's a total double-edged sword. On one hand, using Haskell's parser combinator libraries, things like Parsec or Megaparsec, it feels like absolute magic. It's so satisfying to just snap these tiny, independent parsing functions together to process really complex grammar. But on the other hand, man, it is incredibly frustrating when that beautiful logic just silently fails on you, or worse, spectacularly crashes your whole program. So today, we're taking a deep dive into fixing a very specific, very frustrating parser bug. But we're not just squashing a bug here. We're looking at the journey from having rigid, broken logic to achieving true functional fluency in your codebase. So picture this for a second. You're driving. You confidently turn down a street, cruise for a block or two, and then suddenly realize you're at a total dead end. Now, you don't just put the pedal to the metal and crash your car into the brick wall, right? No way. You stop, put it in reverse, and you make a U-turn. Well, in the world of parsing text in Haskell, your code can hit dead ends too. Except in programming, crashing the car into the wall means your parser throws this unrecoverable parse error. It completely halts execution, fails to compile the text, and just leaves you staring at a messy stack trace. Today, we're exploring a programmatic U-turn metaphor that is literally going to save our code from those fatal crashes and make our parsers infinitely more resilient.
Okay, let's dive into this, the multi-line paragraph problem.
Let's set the stage here. A developer named Ang was building a parser, and they ran into a massive headache while testing input file layouts. Their old parser logic was, well, it was incredibly rigid. It was based mostly on standard Western formatting assumptions, where a new line character is essentially treated as the start of a completely new paragraph. But, as Ang quickly discovered, reality is way messier than that. Take Chinese web novels, for example. If you've ever read one, you know they have these highly specific formatting quirks. In these texts, a single paragraph frequently spans multiple lines, totally ignoring standard line breaks, and they're separated only by full blank lines. So picture Ang just staring at their terminal screen. Their perfectly good parser was dutifully doing its job, but because of these formatting quirks, it was absolutely shredding cohesive, multi-line chapters into disjointed, fragmented sentences. Every time a sentence wrapped to a new line, the parser incorrectly chopped it into 3 or 4 separate disconnected text blocks. They quickly realized they needed to completely rewrite the parsing rules to hunt down and fix this behavior.
So, let's look at how we fix it. Mapping the parsing rules.
How do we actually translate that messy reality into clean Haskell code? We have to establish a new foundational rule for our updated logic. A paragraph is now defined as a sequence of lines that are not separated by a blank line and, crucially, do not start with a header pattern. Now, in plain English, that sounds fairly straightforward, right? But teaching a functional parser to understand this requires quite a bit of structural finesse. Specifically, it brings up the challenge of programmatic negation. Like, how do you tell a Haskell parser what not to parse? You can't just tell it to look for a specific character. You literally have to train it to constantly check its environment. It has to verify that a blank line isn't looming and confirm that a string of text isn't actually a disguised chapter title, all while actively reading the content itself.
Let's walk through this new code logic step by step. Imagine our parser as a character carefully navigating down the lines of a dense text file. Step 1, it confidently grabs the content of the first line. Step 2, it evaluates its surroundings and looks ahead to gather the remaining lines, essentially everything else that belongs to that specific paragraph. In Step 3, once it's gathered all those stray lines, it uses the mconcat function to merge that first line and the rest of the lines together into a single, cohesive paragraph token. And for those of us deep into functional programming, you know mconcat is absolutely beautiful here. It takes a list of values, strings, or text monoids in this case, and gracefully folds them together into one unified whole. It perfectly encapsulates the functional composition we always strive for. Gather the data cleanly and fold it together elegantly.
Now, I want to zoom in closely on step 2, that process of identifying those remaining lines. To pull this off without breaking the entire document, the logic first checks for an end of line, or EOL character. Then, it utilizes a deeply powerful functional concept, a look-ahead function. If you aren't familiar, a look-ahead lets the parser peer forward into the input stream without actually consuming any of the characters. It's essentially scouting ahead. It peeks forward to ensure there are absolutely no paragraph separators present before it decides to merge the lines. This is absolutely vital because we want to completely avoid accidentally swallowing metadata markers. Just imagine a text file that has a string of dashes signifying a scene change, or a massive bold chapter header like Chapter 1. If the parser just blindly ate every line it saw, it would destroy those crucial structural elements. The look-ahead guarantees those markers are preserved safely in the stream for the next parsing function to handle. Because of this, the parser knows precisely when the paragraph actually stops.
Now, what's really interesting about all this is what happens next, the programmatic U-turn.
We have to talk about parser backtracking. This is the ability for a parser to revert to an earlier state if it encounters a sequence that doesn't match its expected criteria, which ultimately prevents those fatal parse errors. And to truly understand why this matters, we have to talk about greediness and consuming input. In Haskell parser libraries, parsers are inherently greedy. When a parser successfully matches a token, like an end-of-line character, it consumes it. It just eats it right up, mutates the state of the input stream by advancing its position, and eagerly commits to that specific parsing path. But what if it makes a mistake? What if it consumes that new line character expecting more paragraph text, but the very next thing happens to be a chapter header? Well, because it already consumed the new line, it mutated the state, it's trapped. It can't process the header as a paragraph, and it can't magically spit the new line back out to reset itself. So it panics, and boom, it throws a fatal error, and your entire program crashes.
When Eng pointed this out in their blog, it was an absolute aha moment for me. They noted, think of try as a programmatic U-turn. If the parser hits a dead end, it reverts to the starting point so it can attempt a different route. This is incredible. In Haskell, wrapping our logic in the try combinator function acts like an isolated transaction block. It essentially creates a completely safe sandbox. If the parser enters the try block, greedily consumes a new line, but then hits that unexpected chapter header and fails, well, try catches the failure. It immediately rewinds time. It reverts the state of the input stream back to exactly where it was before the block even started and just pretends nothing was ever consumed. It unconsumes the new line, giving the parser the elegant ability to safely make a U-turn and pass the baton to the chapter header parser instead.
Which brings us to the bigger picture, mastering parser combinators. This try function really is your ultimate safety net. It enables backtracking from those frustrating dead ends, it prevents fatal commitments after consuming characters, and it literally saves your systems from entirely crashing when stumbling upon unexpected headers. As Eng points out, this is frequently the single most misunderstood part of using parser combinators. Beginners often just kind of assume that functional parsers possess some sort of inherent artificial intelligence, that they'll automatically look at a confusing text file and just figure out the right path to resolve ambiguity. But they don't. Functional programming requires explicit, mathematically precise instruction. Parsers are wonderfully fast and powerful, but they are blindly greedy unless you specifically code in the permission and the mechanism to make that U-turn.
Which leaves us with a final thought to apply to your own daily work. Go ahead and open up your current Haskell projects. Where else in your codebase are you committing to a parsing path way too early? Look really closely at anywhere you're using the many or some combinators. Are there places where a greedy parser might be eating tokens it shouldn't, leaving your program totally vulnerable to a fatal crash simply because a try function is missing? Mastering this programmatic U-turn is one of those absolutely crucial steps that separates novice scripters from true functional programmers. It empowers you to handle the messy, unpredictable reality of real-world data with absolute elegance. So, dig into your combinators, implement those safety nets, and enjoy building infinitely smarter, more resilient parsers. See you next time.